It's just an alignment, a tendency of alignment. Of course, there are many other phases. This alignment may even have a biaxial tendency in the planes which are normal to the uniaxial direction. And there are many other liquid crystalline phases in the literature. Maybe this is the easiest, is the simplest, the most basic one. So I'm going to refer mainly to this phase. Although in the recent 2 or 3 years, I've been interested in phases which are the so-called cholesteric phases which have a modulation along a certain axis. That's my interest nowadays. But I'm not going to talk about this. I'm just going to talk about those simple phases. Okay, let me see whether I can. Okay. If I have time, I may talk about 2 or 3 of those items, and Danilo will cut me from the rest of this list, okay? I'm going to talk about the nematic phase transition, and then I'm going to introduce a model which I call the Meyer-Zalpit-Zwanzig elementary model. This is indeed, I think, the most elementary model we can think about to look at those phases. And one of the first problems that we have looked at is a kind of a model which models a mixture of rods and disks. By the way, this was inspired by a work of Vera. I learned this from her, okay? And then mixtures of uniaxial and biaxial nematogenic elements. We have worked on elastomers, elastic MSZ model, together with Danilo and Alberto Petri also. Okay, we have looked at the field behavior, the behavior of these models of fields. And now we are making some attempts to explain cholesteric phases. That's our more recent program, okay? All right. So let me, I like to quote this sentence from Degene and Prost. It says that the statistical mechanics of fluids is difficult, the statistical mechanics of pneumatics is still worth, even for the simplest models, no exact solution has been worked out. But Degene is Pierre G. Degene is the great name in this area. Not only on this area, he comes from real solid-state physics, okay, superconductors, etc. Is the great name. And there is a famous book he published in this area. Okay, so we resort to quite elementary models indeed. That's our program. All right, the elementary statistical models. I'm going to treat them mostly at the mean field level. By the way, at the time I completed my PhD, it was in the place I was working, it was forbidden to talk about mean field, right? So it's really nonsense to talk about mean field. Very interesting critical phenomena, okay? It was a time of the renormalization group. It was not mean field, but we were also talking about well-defined models for magnetism, for example. Magnetism is an excellent laboratory, okay? Because you do have translational symmetry, you have much more control on those models, on those systems. That's not the case in soft matter. So soft matter, there is no LETs, etc. So mean field should be reasonable, okay? At least from the qualitative point of view, no doubt. Huh? Okay, so in the last couple of years, we have a return to mean field. All right, so those models, they provide connections with phenomenological approach, essentially the Landau-Degene expansion. The Landau-Degene expansion is an adaptation of the famous Landau expansion for the free energy. Landau had communications with God to write that expansion, right? So, you know, extensions of that expansion, the extension of that expansion for soft matter, liquid, it's just the work of Degene. It's known in the literature as Degene expansion. Of course, the coefficients of the gene expansion are written phenomenologically on the basis of symmetry, of some general properties of the systems. And if we write a statistical model, a very simple statistical model, we may make connections between those coefficients and the coefficients in the Landau gene expansion. Well, we have a unified approach to critical behavior. We have an interplay of theory, simulations, and experiments. Okay, and we have suggestions of occurrence of new experimental phenomena. All right, so the first thing I would like to show to you is a phase diagram, which is interesting because there is an isotropic phase on top and two different nematic phases, In between these two different nematic phases, which are really uniaxial phases, one of them is cylinder-like, the other one is plate-like, okay, they are different symmetries. And there is a biaxial phase. During a long time, people thought that it was very difficult to find a biaxial phase. Finally, those people published a paper. They are well-known people in the area. These are people, Yu and Salp. Salp is a well-known name in the area. And this is all 1980s. But this is an old problem in São Paulo. Okay? It's an old problem in São Paulo. I hope Antônio Figueiredo will maybe mention this, right? But I should mention Lia Amaral and Antônio Figueiredo. And even before then, there were people in chemistry, in the Chemical Institute in São Paulo, the Chemistry Institute, who were able to grow these two subjects. It's interesting that this system, this experimental system, is not really it's something which we call a lyotropic liquid crystal. It's a liquid crystal formed by micelles. It's not a thermotropic liquid crystal, which is formed by real molecules, okay? Oh, but this is an interesting paper. See, I'm really putting an emphasis on that region with a nematic phase of type L, nematic phase of type C, the isotropic phase, the biaxial phase, and they all meet in a special point. This special point has been dubbed in the literature a Landau multicritical point. So it should be interesting to look at models with a Landau multicritical point and see what happens. This is one of the first problems I looked at in this area. All right, this is just to show to you that after the publication of this paper by Zalpi and his collaborator, there are many convincing papers to show the existence of a Landau multicritical point in different systems. Some of those systems are not lyotropic, are really thermotropic systems. All right. So this is one of the first papers we worked at, okay? And indeed, I think the first paper we published in 2010 was by a student of mine, Eduardo Carlo, by Danilo, who is here. He can check that, right? So, and myself, we published this paper in 2010. And then, this is an elementary model indeed. I'm going to show you what's the elementary model. It's the most elementary model you can think about, okay? But there is a bit less elementary because I was provoked by different people to say, well, just do a more sophisticated model and see what happens, okay? And one of the editors of the European journal, who is a collaborator of Figueiredo also, okay, provoked that, so we did that, okay? And this is a work of another student, who's a student of Vera, but who worked with me also, it's Eduardo Fontes and Hicks, in 2002. It's a little bit elementary. And let me use this slide to talk to you about what we call the Meyer-Zalp theory. This is not well known. It's well known in the area of soft matter physics. Maybe it's not well known by people in condensed matter physics. I don't know. But if you look at this system, let me see whether I can use this. Is there a pointer? Perfect. Here. Well, this is the so-called Myers-Alp model. If people won't know the Ising model, okay, it's just not going to be. It's just the next step after the Ising model. It's just a model of quadrupoles, the quadrupole interaction. That's it. It's the next step from the Ising model. I cannot use dipole-dipole interactions because in the nematic phases, I have cylinders, but cylinders don't have a narrow direction instead of magnetism, where there is a direction, there's just a cylinder. So I have quadrupole. And what Myers-Alp did in a ball-on paper to propose this interaction is a kind of first step of development, and then do a mean field calculation. And the mean field calculation is the most trivial mean field calculation. In magnetism, we call it the Bragg-Williams approximation, okay? It's to approximate one of the quadrupoles by its average. That's what they did, okay? And here is the quadrupole, and the quadrupole is written in terms of those vectors, Ni, and vectors Ni is the directors of the quadrupole. And I is the site I, and then there is the N in one direction, the 3 directions, and then you have the quadrupole. Okay, and then you do the calculation, and you do the calculation. It is interesting because this quadrupole, the trace of this quadrupole is zero, and there is the solution, the average value. The average value is a quadrupole, and this average value of the quadrupole is the trace is zero. The trace is zero. That's the uniaxial case. Because in the biaxial case, we can break this symmetry minus 1 over S and minus 1 over S. So this is the mean field solution. This is the mean field solution, the usual mean field solution. What's the Myers-Alp model, which we call the Myers-Alp model? Well, what we do is the following, okay? As we don't like to do mean field by hand, just get one of the quadrupoles and take there the average of the quadrupoles as was done traditionally in magnetism. What we do is what people in statistical mechanics like to do. People love to do this. This is by the way, the spin glass model. I shared it with Wikipedia because it's exactly this. So we just sum over all the spins and divide by the number of spins. So this is what we call a fully connected Hamiltonian. So the approximation is in the Hamiltonian itself, right? A fully connected Hamiltonian. And then after writing this fully connected Hamiltonian, we do exact statistical mechanics. No approximations whatsoever. That's what we in statistical mechanics, we love to do this because, we do the approximation and the definition of the Hamiltonian. So this is what we call the Myers-Alp model. The Myers-Alp model is analogous to what some people call the Curie-Weiss model of ferromagnetism. Sometimes it's called the Curie-Weiss model in ferromagnetism, but I prefer the name. It's a fully connected model. This is this. Then we have to calculate the partition function. However, to calculate the partition function, we have to sum of all the possibilities of the components of this quadrupole. Indeed, all the possibilities of the directors, the unit directors, the microscopic directors. So we do an extra approximation. And this extra approximation is the simplest model. It's indeed the simplest model. This is the extra approximation, which I call the Myers-Alp-Zwanzig model. It's a fully connected model. And besides being a fully connected model, here is the trick. We just assume that the directors point along 3 directions only. Instead of having all the directions, we have 3 directions, X, Y, and Z. And this is a model of 3 directions. And here, it's not 6, it's 3, because there is an equivalence between the directions, plus X and minus X, plus Y minus Y. This is the simplest model, okay? It is indeed, it's a special 3-state Potts model. It's a 3-state Potts model. If you think about the states, maybe I should write here the states, the 3 possible states, set of each one of those elementary quadrupoles. So this is our main instrument of work, all right? Instead of looking to more sophisticated model, instead of looking to more detailed models, we are going to look just at this MSZ model. I wrote Z there. That's a tribute to a great physicist in statistical mechanics, Robert Salinas. Because Robert Salinas did this kind of calculation to try to go ahead and calculate the virial coefficients of a gas, of hard rod molecules. And well, he tried to go ahead and calculate those coefficients by doing this assumption that the hard cylinders, I think, of this, hard rods of this gas, of particles, the cylinders were pointing along 3 directions only, okay? So there's a famous work of Swansea, you know, it's a work of the 50s, I believe. You know, nowadays people they count those coefficients, the virial coefficients in the computer, okay? Probably have 30, 40, 50 coefficients, I don't know. Swansea was very happy to have 6 or 7, all right? But anyway, here is the model we work, okay? So let me go ahead and let's see how much Danilo will allow me to go, okay? So if we do the calculations, the statistical mechanics calculations, we really solve the problem, okay? And here is the typical solution of the problem. You see there is a first-order transition. There's a first-order transition. We can calculate the free energy and see that there are 2 coexistent phases, okay? And there is no chance. In all of those models, the transition is first order, and experimentally, the transition is first order in all nematic, most of them, not all, but most of them. Okay? It's the good point is how to change the order of this transition. The transition is first order in those experimentally. Although it's a weak first order transition, but the transition is there, okay? And of course, we can do an expansion. This is the Landau-Dejeuner expansion. And if we do the Landau-Dejeuner expansion, we make the expansion according to the idea of Dejeuner in terms of the trace of the square of the order parameter and the trace of the cube of the order parameter. These are the correct parameters to do the Landau-Dejeuner expansion. We calculate the coefficients in terms of the model. In terms of the model, the temperature, the A is the energy, and you see we can have the 0. We can have a 0, the coefficient may be 0, the coefficient of the second term. But it's horrible because the coefficient of the third term, there is no way to have a 0 coefficient. So the existence of the third term, the Landau expansion, defines the character of the transition, the first order transition. Okay? So we did this calculation. We did this calculation for the fully connected model, and also we did this calculation on the bit lattice. Now, the bit lattice is also a trick that all the people in condensed matter physics used to like the bit lattice very much, you know? They used to like the bit piles approximation, right? But if you formulate the problem on a KLA tree and look at the central part of the KLA tree, so the equation of state is exactly the bit piles approximation. So we really we like to talk about the KLA tree, bit lattice, and solutions on the bit lattice, but you go a little bit beyond the usual mean field approximation. So that's something we checked also, and I checked also with my colleague, André Vieira, who did several works with me, and now he works with Oro Presa, who will show a poster here with fantastic phase diagrams. So, and Eduardo do Carmo. Okay, let's go ahead. We can define another model, which I call a six-state model. This six-state model takes into account the possibility of biaxiality. maybe this is the easiest model to take into account the biaxiality by the introduction of this parameter delta. Parameter delta gauges the degree of intrinsic biaxiality. I call this model, I use the name of Fraser, because Fraser was the first experimentalist to really look at those problems in the calculation to show that there is indeed a stable biaxial phase in this kind of model. Well, we can use this. It's more complicated, just more complicated. Calculations are longer, etc. But we can do this. Okay, this is the 6-state MSZ Fraser model. Okay, it's a paper that we did to show that this model with this constant delta, etc., it does have a biaxial phase. See, it has a nematic phase of one type, a nematic phase of another type. It has a biaxial phase, and it has a Landau point. The transitions are first order, second order, etc. And this phase diagram is bona fide thermodynamically, and it does correspond to the experimental situation. It's almost finished. One moment. All right, this is it. Binary mixtures of intrinsically uniaxial and intrinsically biaxial elements, okay? Well, I hope in this poster by some incredible mixtures will show for let's guess model of this. It's more sophisticated than this, okay? Okay, there are incredible, no, let me go back, because here is I don't have time to go to all the details of those questions, but I would like to talk a little bit about this phase diagram. Unfortunately, I don't have another transparency here, but here you see there is a nematic phase of one type, a nematic phase of another type, and there is a biaxial phase in this phase diagram. This is the paper I did with Danilo. Danilo, let me see whether I explain this question well. The problem is the following, okay? At the time, in 2010, there were two different types of papers in the literature. There was a paper in the literature studying a mixture of rods and discs, etc. Simple paper, etc. And by a guy who is a guy very well known in the area, okay, with a biaxial phase. Showing that's the way to produce a biaxial phase. It's a mixture of cylinder on the oblate, cylinder-like and disc-like, etc. But then I realized that there is another paper by Vera Henriques and her student, Eduardo. Right? And the paper is just the opposite of this. The paper is just the opposite. There was no possibility in this mixture to have a biaxial phase. Well, I'm sure that Vera does calculations very carefully, okay? I checked that paper very carefully, okay? And that's there, okay? Oh, we have in our group someone saying that there is no chance to have a biaxial phase. And then there are papers by Paul Horek, it's a guy, very well-known guy in this area, okay, from the Kent State, saying that there is. What's the problem? What's the problem? And then we realized that when we have a mixture of rods and cylinders, there are different ways to treat this mixture. People from solid-state physics, when they have a mixture, for example, with spin glasses, mixtures of one ferromagnet, they treat the mixtures, they treat the disorder as fixed disorder. The disorder is fixed. In the jargon of condensed matter physics, is the quantity system. So you have a quantity system. Okay, condensed matter physics, impurities are quantity. They have a very long relaxation time. But in liquids, the disorder thermalizes. It gets thermal equilibrium. So its disorder is what we call in solid-state physics is annealed disorder. It's thermalized disorder. And that was the answer to this question, Okay, the article by guys in the tradition of chemical physics, like Paul Morey, was an article with anilid, thermalized disorder. Vera had a tradition of solid-state physics, spin glasses and random fields, I don't know, it's a quench disorder. So the results are different in quench disorder and anilid disorder. So that's exactly what we did. We were able to show that everybody was all right. Those papers are right, the paper of Vera and the other papers, but they are treating disorder in a different way. And then we realized that in the literature there were several attempts to treat a case in between. That's really tough, okay, but there is. We have to use all the formalism of non-equilibrium, etc., to treat in between, a case in between quenched and anilid disorder. That's what we did. And then we realized that a little bit of quenched disorder is sufficient. Now, quenched disorder, there is no Landau point, no biaxial phase, but a little bit of anilid disorder is enough to produce a biaxial phase and a Landau point. So I like this result very much. Maybe we should do this. It's difficult to explain to experimentalists, because there are experimentalists who even argue with me, well, but how do I change the temperature to get anilid disorder? No temperature. Just anilid disorder is different from quenched disorder. Okay? And it's curious, because people in solid-state physics, magnetism especially, they have quenched disorder. That's the way they work. Okay? And quenched disorder, in my opinion, is much tougher than anilid disorder. No doubt, Parisi deserves his Nobel Prize. Quenched disorder is quite tough, okay? But anilid disorder is simpler. Okay, I think I have talked too much. I'm sorry, Danilo. I could talk about other work. I have not talked about other work. I have not talked about work with Petri, but we will have a chance to do it later, okay? And cholesterics, I'm trying to do some. We have been able to do cholesterics with O2 symmetry. That's all right. Okay? It's a generalization of it's a nematic generalization of the old clock models of magnetism. That we did. That is all right. Okay? People forgot to do this 20 years ago. We were able to do. But it's necessary to go beyond O2 symmetry, to do problems in symmetry. O3 is real symmetry. And that's what we should be trying to do. Thank you, Danilo. I'm sorry. It's time.
Thank you, Professor Salinas, again.
Okay.
We have time for one quick question, perhaps.
No time. Okay.
Thank you, Professor, very much for the nice lecture. I was wondering, it's the first time that I see this physics, but I was wondering if I can go to an uniaxial, to a biaxial symmetry when I apply pressure to a nematic phase. Is it possible? Is there something about this?
Specialist is Danilo. Okay? He's talking about pressure, okay?
Pressure, yeah. I don't remember anything that any nematic to biaxial driven by pressure.
It's tough, okay? It's one of the things I would love to do is to allow elastic and to change even the order of the transitions with the application of pressure, okay? This is done in magnetism. I have the impression that it's easier to do in magnetism because the transitions from second order to first order. Here's the opposite. I plan to, to look at problems like this, okay? Also, I plan to use those simple models to explain these nematic phases, exactly by looking at these pressure effects along one direction. Oh, we plan to do it, okay? But it's tough, Okay, all right. Thank you.
Okay, let's thank Professor Salinas again. Then I invite Professor Alberto Petri.
Alberto, aí tem todo mundo. parafernália aqui para...
The universe